Okay, question 15. Demand and supply. We're supposed to find the consumer and producer surplus. So, if we wanted to look at a graph of the situation, demand function here, if we're counting by 50s, starts at 200, has a negative slope. So, something kind of like that. The supply function starts at 50 and has a more positive slope. So, what we need to find is what's called this equilibrium point here. The area above the y value of the equilibrium point, that's called the consumer surplus. The area below the y value of the equilibrium point, but above the supply demand, the supply function, that's called the producer surplus. So we need to find each of these areas. So the first step is to find this equilibrium point. Just like on question 14, the way to find the intersection of two graphs is to set the equations equal to each other. So 200 minus 0.2x equals 50 plus 1.3x. So adding the 0.2 over, we're going to get 1.5. Subtracting the 50, we get 150. So 150 equals 1.5x. And dividing by 1.5, is 100. So the x value is 100. And that's helpful because it's going to give us our bounds of integration. We know we're going to integrate from 0 to 100. But we need the y value of the equilibrium point. So we take 100 and plug it into either one of these demand or supply functions. So I'm going to plug it into the demand function. 200 minus 0.2 is 100. 20% of 100 is 20. 200 minus 20 equals 180. So for consumer surplus, we're going to integrate from 0 to 100. And remember, it's this region up in here, so the upper function is our demand function, 200 minus 0.2x. Let me subtract the bottom function is the y value of our equilibrium point, minus 180. $200 minus 180 is 20, so we're going to integrate from 0 to 100 of 20 minus, now instead of 0.2, I'm going to call that 1/5 x dx. So the antiderivative is going to become 20x minus 1/5 x squared over 2, or x squared over 10, and that's going to be evaluated between 0 and 100. So the antiderivative evaluated at the upper bound, 20 times 100 minus 100 squared over 10. That's the antiderivative of the upper bound. Then we subtract the antiderivative at the lower bound. Plugging a 0 in for both x's, though, is something to yield 0. So this is our antiderivative at the upper bound here minus the lower bound. 20 times 100 is 2,000, and then 100 squared is 10,000. 10,000 divided by 10 is 1,000. So the consumer surplus is $1,000. Now for the producer, that's going to be the integral from 0 to 100, and we're trying to find this area now. So the upper bound, or the upper function, is the y value of the equilibrium point, 180. And we subtract the lower function in this region, this area, is the supply function. So we're going to subtract 50 plus 1.3x. So simplifying and combining some like terms, the integral from 0 to 100, 180 minus 50 is 130, minus 1.3x. So the antiderivative becomes 130x minus 1.3 times x squared over 2. So we evaluate this antiderivative from 0 to 100. So with the upper bound of integration, 100, we have 130 times 100 minus 1.3 times x squared, or times 100 squared. So there's the antiderivative of the upper bound. Antiderivative evaluated as a lower bound is 0 minus 0, which is simply minus 0. 130 times 100 is 13,000 minus, well, let's see, 100 squared is 10,000, divided by 2, 5,000. So 100 squared, 10,000, divided by 2 is 5,000, multiplied by 1.3 is 6,500. And 13,000 minus 6,500 is 6,500. So question 16 is asking to evaluate the integral of e to the negative 2x from 0 to infinity. So it's pretty much 0 to infinity of e to the negative 2x dx. Now just so you have an idea of what this graph looks like, so starting at 0 to infinity, we're trying to find this area. And it appears that the graph comes down and touches the x-axis. It actually doesn't. There's a horizontal asymptote. So there is a tiny bit of a gap above the graph and below the below the graph and above the x-axis. So the area does continue to increase, but as this graph gets closer and closer to the x-axis, the amount of space between them gets smaller and smaller. At infinity, there's virtually no space between them, so we would say that eventually the area is finite at infinity. And this is what was talked about in the last section in chapter 6 that we covered. 6.4 regarding convergence or divergence. So if we are able to evaluate this, we would say that this converges. If not, it diverges. So the formula we learned this formula that when you have this kind of a integral here, where the upper bound is infinity, the formula becomes a limit problem. The limit from b to infinity, and now we replace the upper bound of the original integral with b, from 0 to b of e to the negative 2x dx. Now we got to evaluate and find the antiderivative of e to the negative 2x. So we're going to have to do a small u substitution. If u equals negative 2x, then du equals negative 2 dx. We've got the dx, but we need the negative 2, so I'm going to put a negative 2 here and a negative 1/2 out in front. So now we have negative 1/2 times the integral of e to the u du, which is negative 1/2 e to the u. So going back, we have negative 1/2 times e to the negative 2x evaluated from 0 to b. So negative 1/2 is just the coefficient. So I'm going to pull that out front and evaluate the antiderivative at the upper bound and lower bound with the 1/2 pulled out. So the antiderivative at the upper bound is just e to the negative 2b, and then subtract the antiderivative evaluated at the lower bound is e to the 0 power, and that is just 1. So we've got negative 1/2 e to negative 2b minus 1, and originally we were taking the limit of that as b approaches infinity. So e to the negative 2b, I'm going to rewrite that as 1 over e to the 2b. So as b approaches infinity, e to the 2b becomes a larger and larger and larger quantity. 1 over an increasing quantity approaches 0. So this approaches 0 as b approaches infinity. 0 minus 1 is negative 1. Negative 1/2 times negative 1 equals 1/2. Since we were to evaluate this integral at a finite number, we would say that it converges to 1/2. Now looking at this one, it's a similar thing. We're going to evaluate the integral from 1 to infinity of the natural log of x over x dx. I'm going to rewrite this a little bit to make the integration a little easier. So, integral from 1 to infinity of the natural log of x of 1 over x. Now, you see here that we have an inside function of x inside of a natural log. Typically, we let u equal the inside function, but if we let u equal the entire function natural log of x, then du equals the derivative of natural log, which is 1 over x. So here we have u, and here we have du. So the integral becomes integral of u du which is u squared over 2 plus c, well, we don't need a plus c because we're doing definite integration, but e squared over 2, which is the natural log of x squared over 2. And that's going to be evaluated. Well, we need to use the same limit situation here because the upper bound is infinity, so this is going to be the limit as b approaches infinity, and the upper bound there is b. So we're going to be evaluating this from 1 to b. So the antiderivative evaluated at the upper bound is the natural log of b squared over 2, and then we subtract natural log of 1 squared all over 2, and we're taking the limit as b approaches infinity. Natural log of 1 is 0. 0 squared is 0 over 2. So this is just 0. So really what we need to think about is this. The natural log of b, as b increases, just becomes larger and larger and larger. So this expression, or this quantity here, increases without bound. So it isn't possible to evaluate this infinite limit, so we would say that this diverges.